Okay, here's an experiment for the Hall effect, just to give the whole circuit. So I've got the voltmeter to measure my Hall voltage. I'll move that out of the way. I've got a battery source, obviously. I've got quite a high voltage, so 27.3 volts. Doesn't matter on the voltage, but it's quite high. I'm then running it through a resistor to limit, obviously, the flow. And over here I've got an ammeter, so at the moment I've got on 12 milliamps. Okay, obviously if I adjust the voltage or if I adjust the resistance, I will get different values here, etc. So I'll just use it on that. Now, what we've got going on over here is our actual device. So let me just remove my things, and there we go in our setup. So my current is going to flow in through the top, okay, and out back through the bottom to the battery pack. So resistor, ammeter, part of the circuit, and then back down to the battery. At right angles, I'm going to measure my voltage, okay, and that will vary. The polarity will depend on which direction the electrons are being pushed, or shall we say, the charges are being pushed. So if we are considering positive current coming into it from the top, if I have my current flowing down and I put my field directly into this plate, then what will happen is the positive charge will end up on this side, and this will give me a reading of positive voltage. Okay, so from my circuit here I can see that my voltmeter will be positive if that's where they're going. Okay, so I can work out the polarity of my magnetic field as well. So what I'm going to do is just I'm going to squeeze my resistor on the top of that, and even just putting it on there, you can see in a very rough way over on the left that voltage builds up when I put a magnetic field on it. Okay, and that's very roughly. So let's get some proper readings and see what we can do from there. So let me get a close-up of my setup here. Okay, so there we go. So what I'm going to do is I'm going to adjust the voltage until, because I've got no, so I'm not anything hidden, I have no magnet there. What I'm going to do is I'm going to adjust this so it gives me 0 volts, and I will just adjust the camera again. Try and see, move it back a bit, try and see both at the same time. Okay, so here we go, I'll just move that through. I'll clear out my lead out of the way. There we go. So, voltmeter reading, at the moment, I'll try and get that to 0. A little bit hard to do, but about that. So 0 on the millivolt scale. Here's our decimal place for voltage, so that's 1 milliamp, our lowest unit. So that's the resolution of our meter. Okay, if I don't adjust anything else, that current won't change. That will stay at 12 milliamps. So I'm going to stick my magnet on the top. So that's just a single magnet, which means that although the field's coming out perpendicular, it will start to curve around. So it's the slice itself is only 10 by 5 millimeters, so it's nowhere near as big as this, but again it's not particularly uniform. But you can see already I'm getting 12 millivolts. Now if I just slide in the magnet a pair, so I've got 2 of them, oops, and I'll try and do it without breaking the semiconductor, what you'll find is we should end up with, I'll just show it there, a fairly even magnetic field in the middle. It's right in the middle of that, as you can see from the cross, and I'm getting 184 millivolts. Okay, so I'm just going to put that in my value and take a reading. Excuse me, knock the thing there. 183 millivolts. Let's go that, and I've got 11.5 milliamps flowing at that moment. Okay, now if I swap this around, let me just try and slide the magnet out a second. There we go. And if I swap it over, so I've just turned and swapped north for south, you will see that we get a change on our voltage scale. Now, what happened, I don't know if you noticed it there, but the voltage stayed as it was at 183, 184. So it's now dropping. Okay, so it is quite a hard experiment to do. Excuse me, get it into shot. And get consistent readings. You have to have it at 0 to start with. Okay, so the key is it's gone down. It's got the opposite polarity because I've swapped the magnetic field direction. Okay, I will slot back in my pair of magnets and my numbers start to change immediately. I don't know which way around I've put them, but we're getting 0.80 there, 80 millivolts or so there. If I add in more magnets, okay, and try and do that delicately, then again I get a jump in this. But the jump, and I keep adding them, the jump as it changes down and down and down in this case is not nice and even. Okay, so when we put two magnets together, there we go, we're not actually adjusting this and doubling the flux density. It's not that simple. Okay, so using those values that we've just had, let me get the data in. So that was the equation we derived. Just swapped it around so we can make B the subject of the equation. The voltage we got was 183 millivolts. Okay, our density of charge carriers in the germanium here, sorry, is different. I didn't point this out at the beginning, but this is what's known as a doped type of semiconductor. So it's not pure germanium, it's actually doped to make it, as it says at the top, P-type. So effectively, it's been doped from, or they've infused something from group 3, antimony, I think, or something like that. And what it's done is it effectively has made it better. It's given it some extra charge carriers. The dimensions is that it's a millimeter thick, and the charged electron is 1.69 10 to the minus 19. The current was 11.5 times 10 to the minus 3. Okay, that gives us a value. There we go. That gives us a value of. That gives us a value with those currents. That current and that voltage gave us a value of 2 Teslas. So that was, to make clear, that was the flux density with around about these two pairs of magnets and around about that clearance between them. Okay, so a fairly small clearance. The thickness, as I say, was 1 millimeter, but you have the substrate as well, plastic, so it's around about 4 or 5 millimeters, maybe more like that. Okay, so really quite a dense field. 2 Teslas is a massive number, a huge number.